Recording in progress.
Hey, good morning.
Good morning.
Hi, how are you?
I'm doing good. How are you?
I'm pretty good.
I'm going to have to cut out a little bit early today at 10:30 for a doctor appointment.
Okay.
So I apologize in advance.
No worries. Hopefully you'll be able to catch the recording later.
I will, for sure.
It'll be important because we're going over a new assignment today, and there's a bit of an explanation has to be done to it.
Yeah. Yep, for sure.
How about the rest of you? Oh, there's no one else on Zoom, so it's just you and me. But we got a couple people on YouTube. What do we got here? See people there. Good morning to you. Oh boy, so it's the end of the week for us here, Thursday. Where did we leave off last time? Did we do something like a trim function? Is that what we did last time? I think that's what we did. Let's take a look at where we left off. Yes, so we had just written this function called trim. Takes in a string, and it goes over to the end of the string and then starts working its way backwards here until while it's looking for spaces and new lines. So as long as it's finding spaces and new lines, it keeps going backwards, and then when it finally runs into something that's not a space or a new line, then it just marks that with a null character. And then that essentially truncates the string at that point and effectively gets rid of any trailing new lines that are on, trailing spaces that are on the string. So that's kind of useful for handling user input. Typically, if you ask someone to type in a string like a name or an address, sometimes they might end up putting a few extra spaces on the end, sometimes accidentally, sometimes because they're copying and pasting off of another document and there were spaces there. So, you know, as a computer, it's a good idea to, as a computer programmer, it's a good idea to handle those sorts of unintended human input errors so that you can be a little more friendly to your users. I run into all sorts of situations where, let's say, I have to log in and I have to type in my username and password. And for some reason, I've got either a leading space or a trailing space on my username or my password. And then the system says, can't find you. And it's really hard to see those extra spaces. The trailing ones in particular are very hard to see because they're just invisible. What I have to do usually is click on the username and put the cursor there, and then use the arrow keys to kind of run the cursor back and forth and see if there's anything on the trailing end. On the leading end, it's also kind of hard to see because the word is just indented by a little bit, but usually it's just a few pixels. So again, I kind of run my cursor back and forth over there and see if there's any jumps in the cursor to indicate there's a space there. And I figure, I mean, how hard would it have been for the programmer of that website to just simply trim the input and get rid of those spaces and not have me have to worry about those things? You know, and I digress a little bit, but the other one that always bugs me is handling things like credit card numbers. You know, sometimes you run into a situation where it says, you know, your credit card number cannot contain any spaces. And I'm like, how hard would it have been to just let me put the spaces in like they appear on the credit card and just take them out programmatically? Would that have been so hard? So I think I want to do a couple of variations on this trim function. I want to do one variation where it only trims off the new line character and it retains the spaces. And another version that trims off not only the trailing new spaces, but also the leading ones. So we'll end up with three versions. One that trims off new lines and spaces on the end. This is the one we already wrote. One that trims off just the new line character, and one that trims off spaces on either end. So the usefulness of the one that eliminates only the new line character is so it can be used in conjunction with a function like fgetS that, as you know, puts a new line character on there because that's what the user typed in order to terminate the string. We want to get rid of that new line because it's not usually useful to us. So let's take a look at what we're up against here. So we've got a string. I'm going to draw a rectangle to represent our string. And then inside, we have like hello world. And then the user types in a new line character, and then there's a null there. And we want to get rid of this new line character. Now there's two possibilities to consider here. When you're using fgetS, remember, you pass in, let's see, where can I write this? I'm going to just move this down a bit here. There we go. When you use fgetS, you hand it the string that you want to insert the characters into, and then the maximum length. Let's say it's 50 here. Actually, I'll just put length and then where we get the input from. So usually we're going to put in something like a name here, and then maybe 50, and then standard input. That's usually what we'll put in there as actual parameters. So this 50 you hand in as the length of the array that you've set aside for the user's input. And fgetS is programmed so that it will never exceed that number. If the user types in 20 characters, that's okay, that's less than 50. And so it just puts the new line character in the string and then puts the null character at the end. If the user types in more than 50 characters, then what's going to happen is fgetS will stop at the 49th character, put the null character in, that gives us a total of 50, and then the remainder of what the user typed in is still out there waiting to be consumed by the next time we call fgetS. Okay, so when you call fgetS and the user types in more than the maximum number of characters, what it does not do is consume all the characters the user typed in, but put only the maximum number into the array. What it does instead is it consumes all the characters up to the length, puts in the null character at the end, and then the rest remains out there still waiting to be read in at a later time. Okay, I bring that up because it's kind of a misconception about what happens in fgetS when the user's input is longer than the maximum length. So two things happen. One is, first of all, that new line character does not appear in the string because it hasn't been consumed yet. And also, the unconsumed characters are still out there waiting to be consumed later on. Okay? So those two things happen. And I actually had a student write to me with a question, like what happens in the case where the user input is longer than that maximum number? So in that case, the new line character is not there. But there is guaranteed to be a null character there. Okay, so when you pass in the number 50, fgetS will actually read in only 49 characters, up to 49 characters, and then that leaves one left over for putting the null character in there. Okay, so I guess I brought that up because there is a possibility when you do this that new line character will not be there because the string filled up the entire space and the new line character isn't there. So we have to take that into account as well. Okay, so we're going to make a function here called, let's call it trimNL, trim new line. So I think there's two ways we can do this. One would be to go all the way to the end of the string, and then just like we did with trim, kind of work our way backwards. So we go all the way to the end, look at this null character here, look at the previous character, see if that was a new line character, and if it is, get rid of it. So that's using something like the string length function to pop all the way to the end. The other way to do this would be to just march from the beginning, and as soon as we find that first new line character, and there's only going to be one, right? There's only going to be one new line character at most in the string because that's how the user terminated the string. They hit the new line character, they hit the new line key on their keyboard. Because we could just start from the beginning, work our way towards that new line character. As soon as we find it, just get rid of it. Put a null there. So I think since we're going to have to go from the beginning towards the end anyway, right? Whether we use string length, which goes from the beginning and marches its way towards the null character, or whether we search for the new line character, we're going to have to start at the beginning and go towards the end anyway. So we might as well take that later approach of doing that. Abdul asks, can I use the same trim function that I just wrote? I don't want to do that because in this case, I only want to get rid of the new line character. If the user typed in some extra spaces, I want to keep those. So this one is going to trim only the trailing new line, if present. And this one up here will trim all trailing white space, which includes spaces and new line characters. Okay, so the first thing we're going to do is we're going to walk towards end of string. Stopping at the new line. So let's initialize a variable I, which is going to start at 0 and start going towards the end of the string. And we'll say while s bracket I doesn't equal the new line character, increment I. So it's just going to be this tight little loop as it looks at the ith character of the string, starts walking towards the end, and as soon as it hits that new line character, it stops. And now all we have to do is replace the ith character with a null character, and now we're done. So what this will do is it'll start walking towards the end of the string. It'll stop when it hits this new line character, and then it'll replace it with a null character, effectively truncated the string at that point. Okay. But this version of the trim function has one little bug in it, and that is, what if that new line character isn't found? This loop here is just going to keep going until it hits the new line character. And what if it's not there? Well, in this case, it'll just keep going, right? It'll actually go away. It'll go right past that null character and just keep marching through memory until it either finds a new line character or it walks outside of the memory segment, in which case it'll crash. In fact, why don't we let's go ahead and try this. Let's see what happens. So let's go down here, enter your name. We got 50 characters. I'm going to lower this number. I'm going to lower this to like 20, so it's easier to type in a string that's that long. And then we're going to say trim NL, trim new line, and then we'll see what happens. Oh, I'm missing a semicolon. Where was that? Line 34. How'd that happen? Must have been an accident. Let's try this again. There we go. Okay, enter my name. So if I just type in my name and I press enter, you can see that the new line character that would have been there is now gone. And actually, just so you're sure that the new line character was there, let's go ahead and before I trim it, let's print it out. I'm just going to print it out with some stars around it, just so we can see what's going on here. Okay, do you see it here? Here's my name. And then there's a new line character sitting after my name because this set of stars, the 3 stars here, appears on the next line. But in my printf statement, I had them on the same line. So that means I know there's an embedded new line character in the string. But then after I do the trim NL, that new line character is gone. Okay, I have to duck out of the screen for just a moment to close my door because my dog came in and opened the door. Back. So let's run this program again, but this time I'm going to type in a string that's longer than 20 characters. So it doesn't take much. I just, type in a whole bunch of stuff here. And then the program crashed. So that happened because my trim_nl simply looks for the new line character and it never finds one. So it just keeps marching forward out of memory and then the program crashes. So how do we handle that? How do we get this to not do that? How do we get it to not go off the end of the string?
Well, we could, in the while condition, we could include an or and check for if it's new line or if it's the null character.
Okay. So if the ith character is not the new line and the ith character is not the null character, then keep marching forward.
Right.
So when will this stop going forward? Under what condition or conditions will this stop the loop?
It'll stop at either a new line or the null character.
So if it hits either the new line character or the null character, whichever comes first,
right,
it'll stop. And then line 78, is that okay to do? So if we didn't find a new line character, is it okay to replace whatever we did find with a null character?
No, we'd have to check and see if we're on the null character, or if we're, yeah, we'd have to check and see if we found the null character or if we found the new line.
Well, we know that when we get out of this loop that we found one or the other. Right? That's the condition by which this loop will break. If we hit either the new line character or the null character, then we will break out of the loop. So we're guaranteed when we break out of the loop that we're pointing to one of them, one or the other of them. So is it okay to put a null character in wherever we stopped?
Oh, yeah, it would be.
So what happens? So if
I can't see the code on screen. You've still got the notes,
sorry.
but yeah, we could replace either one of those with the null character and it would be fine.
So that's correct, because if we came forward and we hit the new line character, we'll replace that with a null, and that's fine. If the new line wasn't there, let's pretend that's not there, and we march forward and we hit this null character and we stop, there's no harm there in replacing that with a null character, right? Because there already is a null character. So we could do that, I think. Let's try it out. So I'm going to save this, compile it. So let's put in a short thing. And the new line character was there, and then here it's not there. And then let's put in something longer.
We can't see the screen.
Oh, my goodness. I keep doing that. Okay, so here was the first run of the program. They had the new line, and then it got rid of it. And now a second run of the program where I've typed in something longer than 20 characters. And here's the first printout before we've trimmed it off, and you can see it has actually truncated my string. It truncated it right there. No, not there. Right there. That was the 20th character. So the rest of it is still like sitting out there. And then here, it left the string untouched. So it didn't remove any characters, which might have happened if we had just blindly taken the previous character and just replaced it with a null. So this worked pretty well, I think. Okay, any questions about that one? So let's do a third version. What should we call this? Trim, I don't know what to call this. Let's call it trim all. How about that? The question is, what happened to the rest of the characters? They're actually still sitting in the standard input. Waiting to be read in later. I guess I could draw like kind of a picture here. So here's your program. And then there's kind of like these, I'll draw them as kind of like clouds, right? There's one cloud out here called standard output, and there's one called standard input. And by default, your standard input is connected to your keyboard, and standard output by default is connected to your screen or terminal display. So when your program uses something like printf to send something to the output, it actually goes to standard output. As far as the program is concerned, that's as far as it went. It went to standard output, and then the operating system itself takes care of shuttling that data then over to your screen. But your program doesn't have any idea that's where it actually ended up. And then likewise, when your program reads something in, it's just reading from standard input. It has no idea where that standard input is connected to. But by default, it's your keyboard. And so the operating system handles pulling characters one at a time off of your keyboard and then sending them to your program. And actually what happens is when you call fgets, your program is then halted. It's paused. The operating system turns control over to your keyboard. You type in a whole bunch of characters, and then all those characters go into what's called a buffer inside of standard input. So all the key presses go into that buffer. When you hit that enter key, then at that point, the buffer is now filled with all the input that you typed in, and then control is handed back to your program, and your program now starts pulling characters one at a time out of that buffer and putting them into the string that you had set aside for holding the input. So it pulls one character at a time out of that buffer, and then fgets will stop when it hits that maximum number. Since it was pulling one character at a time out of the buffer, that means that any characters left over in the buffer are still there. So when will they get read in? Well, the next time you call fgets, it'll start pulling characters out of that buffer, and what it'll start pulling in is those remaining characters, plus any new input that's come in. Okay, so we want to write a program called trim all that trims off both the trailing and the leading spaces. So that one is going to be a little bit different. Actually, it's going to be a lot different. Let's say we got a couple spaces at the beginning and a few spaces on the end, and then a new line, and then a null character. So we know how to handle the spaces at the beginning. We can walk all the way to the end and then work our way backwards until we hit something that's not a white space character. and then we can replace the first one of those with the null character. That's fine. But how do we do the beginning? Like, you know, we can't just like stick a null character here, obviously. And we don't want to create a new string because we're not returning anything back to the caller. You didn't see the picture I was looking at here. We don't want to return anything back to the caller because we just want to modify the string in place. So we have to do a different tactic there. And I think the thing to do there is to start moving these characters forward. So take this, so find the first letter that's not a space and then move that into the first position and then start copying the rest of the string. So we kind of have to tackle this in two phases. One is to go and trim off the trailing characters, and the other phase is to copy everything down to remove the leading characters. Which one do you want to do first? Now, if we copy down the, it's not a huge, like, earth-shattering decision about whether we do the leading ones first or the trailing ones first. Both will get the job done. Whether we do the leading ones first or the trailing ones first, we'll get the job done. The only thing that I think of is that if we do the leading ones first, then we're going to end up, you know, copying these down, copying these down, copying these down. And then the ones that are on the trailing end, we'll end up copying those down too. Because we won't know those are the ones on the trailing end until we finally hit that null character on the end. So if we do the leading ones first, we'll end up doing a little extra work because we'll end up copying the trailing ones. But if we handle eliminating the trailing ones first by sticking that null there, then when we do the leading ones later, we can stop when we hit that null character. Okay? Now, the other cool thing here is as far as handling the trailing characters, we've already done that. We already have a function that does that. So can we make use of it? How can we just trim the trailing space, making use of the function that already does it?
We can just call our trim function.
Just call trim. And what do we pass in?
Pass in should just be S.
S, yeah. Right, because that's the name of our string within this function. All right, so done. Took care of the trailing. Let's see, catching up on some of the comments here. So fgetS reads from standard input similar to reading from a file. Yes, absolutely. Actually, standard input is just a file as far as your program is concerned. So reading from the keyboard and reading from a file are exactly the same operation. That's a really good insight there. And when we start learning about files in a few weeks, that could come in really handy. Okay, so trim the leading white space. So we're going to do that by, let's see, we're going to have to scan forward until we find something that's not a white space character. So let's initialize a variable. And then we'll do while s sub I is not is equal to a space or a new line. And a new line is considered a white space character. So let's go ahead and do that. Okay, so we're going to scan forward until, as long as we're looking at spaces and lines, we're going to keep scanning forward. And you know, for completeness here, we could also do tab characters. So if the user hits that tab character, the tab is actually a character, and I think it's ASCII value 9. So it actually is represented in the ASCII table with a numeric value. So as long as we're looking at spaces, new lines, or tabs, we're going to keep scanning forward. And then this loop will stop when it hits something that's not one of those 3 characters. Okay, so now we've located the first character that's not a white space, and now we have to start moving things backwards. Oh, let's see. So we know. So I basically, I'm trying to think this through here. So I is basically pointing at the first character that is not a white space. And we're also going to need another variable to keep track of where we are copying, actually, where we're copying things into. Let's call this, I guess, D for our destination, right? So we're going to take the ith character and copy it into the dth character, and then we'll march those 2 things forward. So now we're going to start marching forward and say, well, the ith character is not the null character. So while we haven't hit the end of the string, copy the ith character into the D character, and then increment D. Increment D. And and also increment I. Okay? So D and I is pointing into the string, D is pointing a few characters behind it, and then we're going to start marching those 2 forward. And then we're going to stop when we hit the end of the string. And I think that should do it.
Won't we have to bring the null character forward as the very last step?
Let's see. Does that get handled automatically by this? I guess it doesn't. You're right. So I guess it stops when I hits the null character, but then it doesn't copy it, right?
Right.
So we'll have to do one last step, which is S sub D is equal to the null character. Okay, so let's type in space, space, space. And a few spaces on the end. Did it work? So here's what I originally typed in. A few spaces before hello. Can't really see the spaces after hello, after world, but there's the new line character, which caused the stars to go on to the next line. And then here, it looks like we still have spaces on the front, and we still have spaces on the end. So, Oh, you know what the problem is? I never called my trim all function. down in main. I just trimmed off new line character. Let's try this again. Okay, did it work? It looks good, right? I had a few spaces in the front, had a few spaces on the end, which you can't see, but I know that they're there because the new line character is there. And then they're gone. All right, good job. I'll pat myself on the back for that. The only thing that I see there that could possibly be improved, and it's really a minor thing, is that once I locate where this ith character is, once I locate where the first non-white space character is, the difference between D and I is a constant. Right? The D and I are both going to start marching forward, but they always remain the same distance apart. They're never going to like change their distance. So D and I go in lockstep. So what I think that means is that we could possibly get rid of one of those variables since they're always a constant offset from each other. You know? So by the time we get to the end of this loop here, the value of I is that offset amount. So let's try going like int offset equals I. And let's call this, I'm going to change the comment here. This is the amount to, well, I'll say distance. Distance. And now I don't have to change this. And I can say, here I can do I minus the offset. Okay, let's see if that works. And then here, this would be I minus offset. I don't know if this has really changed anything because now I'm doing like additions and subtractions, whereas before I was just doing an increment. So, and I still have a variable. But it still works. So I eliminated one variable to increment, but at the expense of having to do this offset calculation every single time. So I don't know if I saved anything there. Oh, Akash has a good suggestion here to clean up the code a little bit. Let me do like undo. Let's put it back the way it was. Okay, this is the way it was before. His suggestion here is combine these three lines together. Like this. I actually kind of like that. It looks clean to me, right? Nice and symmetric. Just make sure it works. Still works. I'd say go with whatever solution makes the most sense to you. All right, if it makes sense to calculate an offset and then just subtract the offset from the value of I as you go through the loop, do that. If it makes sense to have two variables that are incrementing in lockstep, kind of like we've got here, do that, right? Maybe the optimizer will take over and the code will be roughly the same in both cases. There was a question, isn't there some built-in function that will tell you if a particular character is white space? There is. There is a function called isWhitespace, I think. It's in one of the header files. And we could have used that, but I wanted to show you how this is all done kind of manually, so that what's going on underneath a function like isWhitespace is not a big mystery. It's really just doing this. Okay, so we've got three versions of the trim functions. We've got one that trims only the trailing characters. We've got one that trims only a trailing new line if it's there. And then we've got one that trims both the leading and the trailing white space. And this is a really great combination of functions. And why wouldn't you just use that very last one that trims both the leading and the trailing? Because sometimes you do want to preserve the leading and trailing spaces, but you do want to get rid of the new line character. Can we make another function that trims other characters, like trim off like leading punctuation or something like that? I mean, I'm sure we could. In that case, we might want to generalize these functions to pass in not only the string you want to trim, but perhaps another string that contains the kinds of characters you want to remove. I think it gets a little more complicated than I'm willing to dive into at this point. So there's one more function I want to write, and that is a substring search function. So you've got a long string and then a shorter string, and you want to search for that shorter string within the longer string. Let's come up with a longer string. We can do like this is a line from a famous children's book, and nearly every child in the United States knows a line like this from the book. This is one of those children's books that nearly every child in the United States has read and has nearly memorized. And even people like us who are in their 50s still know most of that book. So let's say I want to search for a string within this string. So let's say I want to search for the word not right there, right? So I want to see whether a string contains NOT. So I'm going to basically start a search. I'm going to start from the left-hand side, and then I'm going to check to see, are the first three characters of the string NOT? And if they are, I've found it. If they're not, I'm going to basically move forward to the next step and then check to see, are those three letters the thing I'm looking for? And if they are, I shouldn't have used the word not, because if they are not, then that's crazy. Let's say I'm going to look for egg. So I'm going to look for egg, and if those aren't, I'm going to move forward, and I'm basically kind of like sliding this window forward, and then searching for those letters as I go. So I think I'm going to need two loops. I'm going to need an outer loop that is scanning through the string from beginning to end, and then an inner loop that handles comparing each individual character of the string that I want to look for. And then what should this return? It could either return the index of where it found the string that we're searching for, or it could return a pointer to the string that we're searching for. Why don't we go ahead and have it return an index? So we've got our, we're gonna pass in two strings. One is the big string we're searching through, and the other is the small string that we're searching for. What should we call those strings? Why don't we just call it str and target. So the first string is the string we're searching through, and target is the string that we're searching for within it. and you're right, there is a string function called str string that does exactly this, but we are writing our own version so that we can see how functions like that actually work. So let's start a loop that counts from the beginning to the end of the larger string. So the value of I here is going to be the ith character of the larger string. And then we're going to check to see if the target string matches up with the characters in the larger string. So let's see, actually, we'll do it like this. Let's see, well, j equals I. Target j doesn't equal the new line character. J++. No, that's not going to work. There we go. Okay, so the outer loop is going from the beginning to the end of the larger string. The inner loop is going from the beginning to the end of the smaller target string. And then we'll say if str I plus j is not equal to target j. Okay, so if the jth character of the target isn't equal to the corresponding character in the outer string, this means that the target string is not matching up. If it's not matching up, we can stop our search through the target string. As soon as we hit a character that doesn't match, we can stop searching through that string and we can jump to the next character in the outer string. So we'll just say break at this point. We'll break out of this inner loop and we'll go to the next character. But if we get all the way to the end of this inner string, it means every single character in the string matched up, right? And at that point, we can say, return I. We found it. And then finally, if we get all the way to the end of the outer string, we didn't find it. Okay, so here is str, here's target, we're looking for egg. So the value of I is marching forward through this outer string. The value of j is marching forward through here. And so what we're going to try to do is we're going to match up this character to here, this character to here, and this character to here. And if there is not a match, then we know that the target string is not where we were searching, and we can break out of that loop that's scanning through the target string and move to the next character in the source string. Okay? If we got all the way through this loop for the target string, it means that every single character in that string matched up. And if they all matched up, it means that we found the target string. And we can just return the location where we were searching in the outer string. And then if we got all the way through the outer string and we never returned out of that loop, then we know that we never found the target string, and we're going to return -1 to indicate that it's not there. Actually, let me just do this. The source equals 50. Let's just go, I do not like green. That way I don't have to type in the string every single time.
Can't see your screen.
Oh, sorry. So I've got my source string. I do not like green eggs and ham. I ask the user to input a target string. I'm going to use fgetS to read that in. And then I'm going to call my search function, pass in the source string and the target string, and it tells me where it found it. And then I'm just going to print out where it found it. And it could print out -1. Okay, target string. Let's search for egg. And it says it found egg at 0. That's totally not what I expected to find for it to return. I expected it to return something like 20 or something like that, and it returned 0, which means that it thinks it found it at element number 0. Oh, and
It also looks, oh, sorry, Mary, go ahead.
no, go ahead.
Oh, so, what if like in the inner for loop, instead of integer j equals 0, you do integer j equals I? Would
Right
that
here?
work?
Right
Yeah.
here? I could do that, which means that this would just be j here. But then the reason why I changed that when I was coding this up was because now as I'm searching through the target string, j no longer would point to the correct character in the target string.
Oh,
Right? Because
okay.
if I is like 20, right, but the target string is only 3 characters long, then it's searching off the end of the target string.
I see.
And so that's why I decided to change this back to 0 and then put I plus j here, just so that both of these numbers here are definitely pointing within the strings themselves.
Looks like your target string is including the new line character.
Oh, so that is true. I called fgetS here, but I need to trim that off because my source string doesn't contain that new line character. So what would be the best trim function to use? Should I use trim
Trim new
NL,
line.
or trim all?
I would just trim the new line
Okay, what's your reasoning behind that?
in case they're searching for white space.
Oh, so in case they are searching for a space, we'd want to be able to search for that. Okay, I agree with that. Let's try this again. Oh, trim, oh, it's a capital letter. All right, target string, egg. Still returns 0. What's going on here? So the only reason it would return 0 is if it hit this return right here. Because otherwise we have a return of -1. This is the only other return. And so why would this return a 0? So that means we're still at the first iteration of this loop here, and it also means we got all the way through this.
It's because, let's see, as soon as you break out of that inner for loop, then it returns whatever index it's at.
Oh, yeah, so the break means get out of this inner loop here. Huh, so how do we fix that? So if we broke out of this loop, it means that the letters didn't match up. And then we don't want to just return I at that point. We only want to return I if we got all the way through this loop. If we got all the way to the end of this loop. So maybe we need an if there. We got like if what? Something. So how do we know whether we got all the way through this loop to completion or whether we broke out of the loop early?
So we could check and see if we're on the new line and on the null character in the target string.
Well, the problem there is that our J only exists within the loop. So we can't look at it after the loop finishes. So maybe we need another variable to just indicate some kind of, like, did we complete the loop or not? Maybe int, I don't know, aborted equals, I don't know, aborted, int, didn't finish. Okay, so if we aborted out of the loop, we'll set this flag to 1. And if that happens, then we will just go to the next iteration of the outer loop. If we did set this to, if we didn't set this to 1, which means we got all the way through the loop, then we'll go ahead and return I. Okay, target string, egg, 20. I was totally guessing where the egg occurred, but when I said 20 earlier. Let's search for something that's not in there, like hello. Okay, -1, that's good. Edge cases would be to search for something that's maybe at the beginning or at the very end of the string. Let's look for I. Oh, no, I right here. Okay, found it 0. That's good. And then let's search for ham. Okay, found it all the way at the end. That's good. Let's search for exclamation mark, which is the very last character in the string. That seems good. There is actually one bug with this program. It's actually a fairly serious bug with it. can you figure out where this program is going to run into a serious issue?
Seems like we could walk off the end of the source array.
When would that happen?
If we get all the way to the last character of the source array, and then we go to test it against the target array, and as we move forward through the target array, we're going to walk off the end of the source array.
So this could happen if the thing that we're looking for, the target we're looking for, overlaps the end of the source array. Right, so let's say I'm looking for ham, 2 hams like that, or ham, egg, something like that. I guess after looking at this, I'm no longer convinced this is a serious bug, but we'll see. We'll see what happens. Well, that's what it should return. Okay, so maybe it's not a problem, and maybe the problem is because remember last time I said that what we were doing? We were doing something where it was like searching for it was like searching for the word or, right? And we said there might be a problem because what if the or is like all the way at the very end, and we end up looking one past the end of the string, right? And that could be a problem. But we ended up saying that's not a problem because there's a null character sitting there. So we're guaranteed there's always going to be at least one more character to look at in our string. And so that's why I think it's not a problem here, because when we look for this E after the exclamation mark, well, that E is going to match up with that null character that's sitting there, and it's not going to match, and the loop will jump out. So if there wasn't that null character sitting there, yes, this would be a problem. We'd end up walking off the end of the array. But the fact that the null character is sitting there is kind of like our saving grace, where it is now going to try to match up the E with the null character. It's not going to match, and at that point, the loop will jump out. So I guess this ended up not being the problem like I thought it was going to be.
Yeah, that makes sense. I wasn't thinking of that character there.
If we were writing this in Java, yeah, that would be an issue, right? Because Java does not put a null character at the end of its strings. What Java does is, you got something like public. It's easier to just write this over here.
I have to leave for my appointment, so I'll have to catch the rest on the video later.
So here's what Java looks like. String. See you later.
All right.
Then you have character str array, and you have int length. So in Java, a string is just a class that has an array of characters and a length. And so the array of characters is not terminated by a null in any way. It's just an array of characters. And so if you try to do something similar, try to do some kind of string search function in Java, you could end up walking off the end of the array, and then the program will crash at that point or give you some kind of exception. So the fact that there's a null character in C helps guard against walking off the end of the array by one character. Now, if you walk off it by more than one character, then you got a problem. But if you just look one character past the end, there's going to be a null sitting there. Okay, let's see where we are. So we've written 4 functions. One we wrote last time, the trim trailing white space characters. Then we wrote one to trim off a new line character if it's there. And then we wrote one to trim off both trailing and leading whitespace characters. And then finally, we wrote a function to search for a substring within a larger string. And a lot of these functions already exist in the standard C library. The one to search for substrings already exists. The one to compute the string length, already there. The trim functions, or the trim newline function, is not there, but you can do it very easily with a couple of the built-in functions. You can do one that just searches for the newline character, and then you can just simply replace that with a null character. So a call to one of the search for a character within a string will handle that for you. So almost all of these have counterparts in the built-in library. What the library doesn't have is things like count uppercase. That seems like a specialized thing that wouldn't be a nice general purpose function. The one for truncating after the first word also is fairly easy to do. You just search for a space, and then once you find the space, you just replace it with a null character. That can be done with one of the built-in functions. And so my purpose here in writing these functions, these string handling functions, is just to show you that the built-in functions are really no more complicated than what I've shown you here. They're just basic loops that start at the beginning of the string and march toward the end of the string as indicated by the null character, and just do some stuff along the way. So the real ones that are built into the standard C library are really not any more fancy than the ones that we've written here. So the question is there any way for some people to join the Zoom session? So I'll answer that. And I'm streaming on YouTube and on Zoom. On Zoom, those are my students who are actually enrolled in my course at my college. And so they're my primary audience. I'm speaking, if they ask a question, I'm going to answer them first because they're actually enrolled in my course and they're the people that I'm primarily speaking to. Folks on YouTube, I'm glad to have you along, but I'm streaming to you and making this content available for free. And when I do get a chance, I look at your comments and I respond to them as well. But the voices you hear are people who are on the Zoom, and unfortunately, I'm reserving the Zoom for the students in my class. So I think that's it as far as writing these string handling functions. Why don't we take a little break, and then when we come back, I'm going to show you the next programming assignment. And we'll talk about that. And that's going to be a fun one, where we're going to be trying to find JPEG images inside of a what's ostensibly a corrupt SD card. Okay? So I'm going to pause the Zoom video, but I'll get a chance to talk to the people following on YouTube.
Recording stopped.
How long does the break last?
Oh, about 10 minutes. Actually, I'll play around with this a little bit. Oh, nothing there. Never mind. I'll do it this way. There we go. So what's your question here? Treating the memory as an array of characters and doing the search substring? Looking back at your comments, I see now when I talked about the find or function and walking one character off, you were actually kind of leading me to the actual what I was talking about, which was that null character on the end is guarding against looking one character past the end of the array. So very good. You remember from last time. Did we do the string compare function? No. No, I'm not going to do all of them. I just wanted to do a few of them, just to kind of give the idea about how they work. But in a couple of weeks, there's a chapter in the textbook that's devoted specifically to string handling. I wanted to do these not as specifically about string, but about arrays and indexing into arrays and passing pointers back and forth. When we get to the actual chapter about strings, then we'll talk about things like string compare, string searching, what are the other ones? String copy. We'll get to those later, okay? My find string, is that kind of the same as grep? Pretty similar, except that grep does regular expressions, which means you can search for a pattern within a string. Mine is just simply searching for characters. So in that case, it's more like, there's a version of grep called fgrep that only searches for strings. It doesn't search for patterns. And so I guess mine would be similar to that in that respect. So when I introduced this assignment, some of you might recognize this assignment. It's very similar to one that was done in Harvard's CS50 course a couple of years ago. I saw that assignment and went, wow, that's a really cool assignment to do. And so I adapted it for my course. Why do regular expressions take a long time to compute? Because they're actually a little language unto themselves. So they have to go a phase, when you use regular expressions in your program, they have to go through a phase where they are compiled and then executed by a little virtual machine within your program. Take my discrete structures course towards the end of the semester. So starting in April or so, we'll talk about finite state machines and regular expressions, and you'll see all the work that has to go into executing a regular expression. Can we take the course from India? Oh, I mean, like, can you register for my course? I guess I don't see why not, although you would have, the way the fee structures work, you would be an international student, and then you would have to pay the international student rate, which is higher than the California resident rate. But otherwise, yeah, I'm sure you could. So if you specifically need credit for the course, that would be the way to go. If you don't need credit for the course, then just follow along on YouTube. And by credit, meaning you actually need a something on your transcript that says you took the course, you got this grade in the course, something you can show to that you actually completed the course. I used to teach a course on databases. I was up till about 8 years ago. I really liked that course too. I used Postgres as the database because I really liked that particular database management system. And we learned the syntax of databases, plus a lot of the stuff that surrounds databases, like normalization, stored procedures, how to interface with not front end, but web scripting languages like PHP. So to me, that was a fun course to teach. And in part because she's got a really huge variety of students in that course. We'd have the traditional college-age students who were taking that course as part of their major, but we also got older students who were coming in because they work in the IT field and they just need to learn about databases or learn more about databases because maybe they've been, in some cases in the IT field, your manager may say, hey, you know, our new project is going to be using databases. I need you to learn about databases really quickly. Like, you know, get yourself familiar with them. And you might have come out of a university and not know anything about databases, at least in the past. These days, it's pretty much almost assured that you're going to take a database course of some sort. But in the past, you might not have learned those things, or it may not have been part of your training at all. And now suddenly you're thrown into using databases. So we got a lot of adult students in the courses. And that was really nice to have a wide variety of kinds of students in that course, because you get, you know, a huge variety of expertise and knowledge areas. And it was just a fun course to teach. I do have a few videos on my channel left over from when I taught that course. Just a few videos about things like doing database transactions and what else do I have on there? I'm trying to remember. Well, search through my channel, you'll find out. And you can see the vast difference between the quality of those videos, which were done 10 years ago, and what I do now. Oh, let's see, how many people do we have here? We've got, oh, there's only one person in the chat. But it looks like we've got at least 9 people watching. Oh, you found it. Database transactions, part 3, ACID and isolation. Yeah, so I think there's 4 or 5 videos in that series. I know I've asked this in the past, but we got some new people on here. Where are y'all from? Austria? All right. Earlier in the session, we had someone from Italy. Oh, Nigeria. Somewhere in the Middle East. India. Sri Lanka. Wow. Okay, another India. What is this? From what? Dimension C-137? Is your username Eugenum? Is your username a reference to an anime show? Oh, it's a Rick and Morty reference. But is your username a reference to an anime show? Rick and Morty is not like in my repertoire of stuff that I watch. I'm sure if I asked my son, he would immediately know what that was. But ah, okay. Ashamed of it. So if I said bubblegum crisis, would that, did I hit the nail on the head there? Oh, wait, did I get it? I'm waiting expectantly to find out. Oh, it's a reference to genomes. All right, well, so it wasn't what I thought it was. I thought for sure it was. I got something to show you here. For those of you old timers. Thought it was from this anime, Bubblegum Crisis, from the 1990s. They fight against their enemy is called Genom, so I thought that's what you were referring to. I was going through all the stuff in my house. I was like, oh, there's stuff that, you just need to declutter the house. So I ran across the old CDs that I had picked up when I was in college. I used to be into this stuff. Like, who even listens to these anymore, these spinny things? Do I watch anime? No, my kids do. but I used to be totally into it. That was back in the 90s. Back when anime was not nearly so prevalent as it is now. I'm not familiar with that one. Attack on Titan. It's a new one for me. But I mean, there's so much anime out there now that you could probably mention just about anyone that the young kids don't know, and I probably don't know it. I mean, of course I know about like Yu-Gi-Oh! And I'm blanking out now. Pokemon and stuff like that, but all the other stuff, don't follow it so much anymore. Okay.
Recording in progress.
So this week's assignment is called CSI, Computer Science Investigation. And the backstory here is that I came up with this assignment back long before the pandemic. And so the story here is I was walking around our campus, taking pictures using my point and shoot camera. And then when I got home, I took the SD card out and I popped it into my computer. And it said, the card, it cannot be read. Would you like to format it? And of course I said, no, I don't want to format it. So when an SD card in a camera gets corrupted like that, it's not like it just gets completely erased. It just means that there's something about the directory structure that the computer can't make sense of. One or more bytes or bits in there have been flipped to the point where it can no longer correctly comprehend the data structure of the files that are on the SD card. And it doesn't matter whether it's an SD card or an SSD or an actual real hard drive. It's the concepts are all the same. And so if you say, no, I don't want to format this card, it won't zero out any of the data. The data is still there. It just needs to be found. There's a whole career out there called forensic investigators, particularly computer forensic investigators. And these people come into maybe a crime scene or where a suspected criminal might live or work. And their job is to grab the data off of the computers that this person was using, and hopefully you can find some evidence of the wrongdoing on there. But what these investigators look for also is, well, let me back up. If you are on your computer and you drag a file to the trash or the recycle bin, and then you say empty the trash or recycle the bin, it doesn't actually, in most cases, delete the file. And by delete, a computer doesn't actually take the file and physically remove it from the storage device. Nothing actually ever comes out. All it does is it just marks in the directory structure that the space on the storage device is now able to be reclaimed. So it doesn't actually go and zero out all the data. It doesn't erase the data. It just simply marks it as being quote unquote deleted, so that the next time you go and create a file, it just recycles that spot on the storage device. And so what these forensic investigators can do is go into a hard drive or an SSD and locate all the files that have been quote unquote deleted. And even if you format a hard drive or an SSD, if you use the quick format option, it doesn't even zero out the data there. It just marks the disk as being formatted. Right? And I put it in quotes here because, again, it doesn't really actually destroy any of the data. It just marks the directory as being empty. And now you can start putting files into it. And so a forensic investigator will take a hard drive. They'll probably pull the hard drive or SSD out of the computer, physically remove it from the computer, attach it to a device attach it to another computer, And then that computer pulls the bytes right off of the disk or the storage device. And that's called taking an image of the disk. So it's all the bytes on that disk, but it's no longer actually a storage device. And then you can write a program or a variety of programs to go and investigate what's there. So even if a file has been deleted, but the data is still there, you can recover it. So our job, your job, is to write a program to go through the image, the contents of this SD card, and find the JPEG images, pull them out, and save them as files that you can then view and see what they are. So first, let me tell you a little bit about how storage devices, whether it be an SD card or an SSD or an actual disk drive, how they actually store the data on the physical media itself. So you can really think about a storage device as just being an array of bytes. The array starts at 0 and it goes up to whatever the capacity of the device is. In fact, I've got some storage devices back here. I'm just going to pull 2 of them out. So here, this is a standard desktop disk drive. I pulled the lid off of it so you can see what's inside. We've got these spinning platters. They're highly mirrored surfaces, along with these read-write heads that go back and forth. And there's actually in here, I think there's 3 or 4 platters in there. So the platter spins at a high speed, and then these arms move back and forth to access the data that's on the disk. And then here's one that's a laptop sized. Again, cover's been removed. We've got a spinning platter, and the same read-write heads are just a little bit smaller. You can see, one's big, one's small. So you got this platter, and it is divided up into kind of pie-shaped pieces. Oh, that's terrible there. Pie-shaped pieces. Each one of these is called a sector. And then because you've got this head that moves back and forth, it traces out concentric circles on these platters. Those are called tracks. Okay, again, this is so sloppy. Right? So these circles are called tracks, and then these pie-shaped pieces are called sectors. And so each one of these pieces of a track within a sector is called a block. Okay, so this pie-shaped piece is called a sector. And then the circle here is called a track. So when you combine them together, you get tracks within sectors, and those are called blocks. So conventionally, over the history of computing, it's been decided that a block is going to be 512 bytes. And it's remained that way for decades, as far as I know. That the standard size of a block is 512 bytes, half a kilobyte. Now let me catch up on the chat here. So when you're doing this forensic investigation of a quote-unquote formatted disk, yes, you might find little bits and pieces of stuff that you've deleted. And that's what these investigators might look for, is maybe evidence of files that the perpetrator wrote at some point, thought that they had deleted, but the data is still there. Could you find old pictures from websites you visited months ago? Mm-hmm. Yep. Okay, so the blocks on a standard spinning disk drive are 512 bytes, and so the blocks on a non-spinning disk drive, like an SSD or an SD card or a compact flash card, are also 512 bytes, but now we can just draw this out as an array of bytes, like up here at the top. And so we'll split this into blocks that are each 512 bytes long. This is 2, 3, 4, 5, 6. So each one of these blocks is 500 bytes long. So another thing you need to know is that whenever you create a new file, and it doesn't matter whether this is on a desktop computer or a laptop or an iPad or a tablet, whenever you store a file onto the storage device, that file will always start at the beginning of a block. So if I create a very small file, let's say it's a 50 byte file, a very small file, the computer will scan through the disk looking for a free block, a block that has not been allocated to some other file. And let's say it finds block number 5 here, and then it will store that 50 bytes, on the first 50 bytes of that block. So a new file will always start at one of these block boundaries. Okay, and so this has a couple of side effects. One is it means that if a file is smaller than a block, it will still essentially use up a whole block. Okay, so the minimum allocation size for a file is 512 bytes. So if a file is smaller than that 512 bytes, it'll occupy the first 50 or so bytes of that block, and the remaining 462 bytes of that block are essentially wasted space. They're not going to be used by some other file. They're only going to be used, they're just free space. And that space between the end of the file and the end of the block is called slack space. Right here, this is called slack space. And that slack space might create, as someone said, bits and pieces of a file that had existed in that block before this new one was created. So a file might have been written to the disk, occupying most of, if not all of a block, and then that file might have been deleted. But remember, it doesn't delete the data, it just simply marks that block as now being free to be recycled for something else. And then a new file came in and overwrite, let's say, the first 50 bytes of that block, but the remaining 460 or so bytes are still there and still contain the data that was there before. And so a forensic investigator might be interested in the data that's in that slack space, because it might contain little bits and pieces of evidence that isn't normally visible. Okay, but so that's a little bit about what forensic investigators do. They're interested in writing programs that analyze the contents of a disk, but they don't just look at the files that are visible, that you can see in the directory structure. We also look for the files that aren't visible, the ones that were there before and have now been deleted or formatted. And so this gives us a little bit of insight about how we can recover the JPEG files that are on the image of this SD card. So the one thing we know is that a JPEG image is always going to begin at one of these block boundaries. So if you're searching for a JPEG image, you never have to look in the middle of a block to find where one of these things start. They're always going to start at a block boundary. And that's the case not only for JPEG, but any file on a storage device. What about files that are longer than a block? So if I've got a file that is, let's say, 1200 bytes long, it might start here at the beginning of block 1, and 1200 bytes means it's going to fill up all of that block, it's going to fill up all of the next block, and then a little bit of the third one. So a file like this will begin at a block boundary, and then it will extend all the way through some subsequent blocks, and then end most likely in the middle of another block. And then again, you've got some slack space between the end of the file and when the block actually ends. So are files smaller than 512 bytes wasteful? Yeah, they're a little bit wasteful, but you don't typically have files that are that small, so you don't waste a whole lot of space. And on a modern storage device, you've got billions, billions of blocks that you can use. And so yes, there's going to be some wasted space, but the trade-off is, do we keep track of each and every single little byte on the storage device, or do we just split it up into blocks and waste a little bit of space?
So I kind of have a question about this. It's kind of off topic. So I'm taking an IT class, and we learned about disk defragmentation.
Yeah.
So is that like, because I know I've done that on my computer. Is it, it writes data different to save space. Would that eliminate like would it, like the space between, like if a block is not being used all the way, would it make it used, or how does that work?
No, that's a different issue, but
Oh, okay.
but I'm glad you brought it up. So on on your Windows computer, there's usually a button there to like defrag or defragment your hard drive. One thing is, if you have an SSD in your computer, a defragmentation doesn't do any good at all. So what defragmentation is to make your disk drive more efficient. The problem here is if you have, and again, I'm going to draw this as a long array of blocks. Actually, I'm going to make my blocks smaller so you can see what's going on here. So let's say you have file A uses 3 blocks, and file B uses 4 blocks. So A goes here, and then B goes here, and let's say C uses 2 blocks. So here's file C. Okay, so far all of the files are not fragmented. They're all occupying contiguous blocks on the storage device. But now what happens if somebody deletes file A? Remember that when you delete a file, it doesn't actually go and erase the contents of those blocks. All it does is it marks those blocks as now being free and able to be used by something else. So we're now going to just basically mark those blocks to say you can now recycle those blocks for something else. So now the user creates file D. And let's say that uses 5 blocks. Where should file D go? Now, one place to put it would be over here at the end. Okay, but these 3 blocks are still free and able to be used. So what the operating system does is it now splits the file up into 2 different locations. It puts part of D up here where A was, so 3 of the 5 blocks it needs, and then the remaining blocks go somewhere else on the disk. So now the file is fragmented, and it does keep track. There's little pointers from block to block to tell it where the file is. So it knows that file D occupies block 0, 1, 2, and also blocks, I don't know what this is, 8 and 9. So it means that if your computer wants to access file D, it has to jump to block 0 and get 3 blocks, and then jump over to block 8 and get the remaining 2 blocks. And that makes for a spinning disk drive like this, that's less efficient because now the head has to move to 2 different places to get the contents of that file. So when you defragment a hard drive, what that does is it rearranges all the blocks for the files so that they're contiguous again. So what the defragmentation process might do is take these 3 blocks for D. I might actually move these 2 over and then take these 3 and move them over here so that now they're contiguous again. Okay, and it might take, let's say, file C and move that over here to fill up that space that D used to take. So it moves the files around on the disk so that now all the blocks are contiguous again. And that makes accessing the files a lot faster because that head now physically doesn't have to move to a bunch of different places to get the contents of that file. The reason why it doesn't matter for an SSD is because SSDs don't have moving parts in them, and it's just as fast to access one part of the storage medium as it is to access any other part. Since there's no moving parts, there's nothing to wait for. And so defragmenting an SSD not only doesn't make it more efficient, because it's already as fast as it possibly can be, but it also, and unfortunately, subtracts from the lifetime of the SSD. Because you're moving data all around, each one of those blocks on an SSD has a fixed lifetime. It may be good for only, let's say, 100,000 reads and writes to that block. After about 100,000 reads and writes to it, or I should say writes to it, after 100,000 writes to it, that block is now completely exhausted and can no longer be written to and has to be marked as bad at that point. Can't be used anymore, unusable. And so if you're moving a lot of data around on SSD, you're subtracting from the life of each one of those cells. So you don't want to defragment an SSD. You don't want to defragment an SD card. You don't want to defrag a compact flash card. So anything with not moving parts in it, you don't want to defrag on. But for moving part disk drives, defragmenting can make it a lot faster. So does that answer your question?
Yeah, that does.
Okay.
Thank you. I like pulling the same topics from different classes.
Yeah.
So.
The reason why it's important for this assignment is I had freshly formatted the SD card, which means that all of the files that you're going to be recovering are going to occupy contiguous blocks. You'll never run across a file that is in 2 or more places. Okay, so for this assignment, this will help you a lot because once you find the beginning of a JPEG, you can just scan forward to find the end of it, and you don't have to jump around. Are block and block sizes hardware defined or file management system defined? I believe they're defined by the hardware. So when these disk drives are manufactured, the computer will send it a signal like read the data from block number 12. And so the disk drive knows that it has to move the head, let's say, to this position on the disk drive, and then it has to spin the disks until block number 12 comes into view underneath the head. And so the disk drive knows about the size of blocks and therefore how to move the physical moving parts in there to get to that block. So it already knows about the size of blocks, and so it's defined by the hardware. Okay, so looking for these JPEG files. JPEGs are a nice file format because they have a structure within them. So in addition to the pixel data, there's also other information about the file. There's things like what camera was used to take the picture, what are the dimensions of the image, what colors are used in the image. Let's see, what else is in there? So regardless, there's different pieces to the JPEG file. And so each of these pieces has a little marker inside of the file. And they're 2-byte sequences, 2 or 4-byte sequences. So at the beginning of a JPEG, particularly ones that were taken by a camera like mine, at the beginning of a JPEG, there's always going to be a 4-byte sequence. And that 4-byte sequence is the bytes 255, 216, 255, 224. So those 4 bytes always appear at the beginning of a JPEG. And that 224 on the end could be either a 224 or a 225. So all JPEG images begin with one of those 2 4-byte sequences. If a file starts with a byte sequence that's not one of those 2 things, then it's most likely not a JPEG image. So this is how your operating system is actually able to tell that a file is a JPEG that it can view on the screen, is it looks for that 4-byte sequence. If the file doesn't contain those 4 bytes, it says this is not a JPEG, I can't view it. It actually doesn't matter at all what the file extension is. The file extension is really just there for us humans to be able to tell what the file type is. But the operating system itself looks for that 4-byte sequence. If it's not there, it rejects the file, says that's not a JPEG. Okay, so all JPEGs start with one of those 2 4-byte sequences, either 255, 216, 255, 224, or 255, 216, 255, 225. And so that last byte just depends upon what kind of camera was used to take the picture. Other kinds of files like PNGs or video files, they have different byte sequences at the start. And so those are really markers to let the operating system know what type of file this actually is. Text files don't have those markers at all. They just start with text. So most other files have some kind of identifying byte sequence at the beginning of the file that tells the operating system what kind of file this is. Okay, so JPEGs always begin with one of those 2-byte sequences, and they always end with a 2-byte sequence. So JPEGs always end with 255, 217. And this is all detailed in the assignment here. Okay, so here's kind of a picture that shows you that the start of the JPEG file starts with one of these 2 4-byte sequences. And then there's the image data in between the start and the end sequence. And then the end of the file ends with 255, 217. So if you can find a file in this SD card image that begins with one of those 2 4-byte sequences and ends with that 2-byte sequence, then you know you've found a JPEG. It doesn't matter what the name of the file is. It doesn't matter what the file extension is. If you can just find all the data in between that start and end sequence, then you know you've found a JPEG image. So that's what your program is going to do, is you're going to scan through this giant array of bytes, and you're looking for that 4-byte sequence. When you've found that, you know you've found the start of a JPEG file. And then you're going to start scanning through to look for that ending sequence. And when you find those, you know you found the end of the JPEG file. And everything in between, including those sequences themselves, is the JPEG file. And then you can say, take that and write it to a file on our file system, and then you can view it in your browser. So it looks like an easy task. And it could be, except for a couple of twists. The first twist is this sequence, 255, 217, it marks the end of a JPEG, but it could also be valid image data, right? That byte sequence there could also appear somewhere in the middle, just because, the image data is like pixel colors, right? And so 255, 217 are valid, like, red, green, blue values. So you might run across those, that sequence somewhere in the middle. So one of the things that your program needs to do is distinguish between a 255, 217 found in the middle and a 255, 217 found at the end of a file. Okay, so there's a couple of things that are going to help you here. First, remember that files always begin at a 512 byte boundary. So that means this 255 sitting at the beginning of the file is always going to be found at a multiple of 512 in the file. And the second thing is, since I initialized or formatted the SD card before I went around and took pictures, when you initialize or format the card, and I did one of those low-level formats that completely erases the card just to ensure there was nothing on it, it zeroes out all the data on the card. So when I do a low-level format, it writes a whole bunch of zeros to the card. The whole thing is full of zeros, and then it starts storing the images on them. You could use that to your advantage to help you distinguish between the marker at the end of a file and the marker in the middle of a file. Okay, so let's go over the starter code. So I've given you a program called recover.c and then the image of this SD card that I took. You can download both of those to your environment. And let's go ahead and do that. So I'm going to download this. Here it is. Actually, what you can do is you can just highlight this and you can just copy the whole thing and then go over here, create a new file, and just paste it in. And then you will also need to download this card.raw file right here. That'll download it to your computer, and then you'll just drag and drop that into your programming environment, and then that file will be available there as well. If the drag and drop doesn't work for some reason, like the file doesn't appear, then refresh the page. And you'll probably find that you just need to log in again. And then once you do that, the drag and drop should work fine. Okay, so let's go and look inside this program. There are some functions that I've already written for you. First one is called read card. You give it the file name that you want to read, and then it will return to you an array of bytes. And here I'm using a type called uint8_t. This stands for unsigned 8-bit integer, and the T stands for type. So this is an unsigned 8-bit integer, which are ostensibly just bytes, right? So it's returning to you an array of bytes. But whenever you're working with arrays, you need access to the array itself, but you also need to know how long the array is. And since this is being created, this array is being created for you, you don't know how long it is. So this read card function needs to be able to pass back 2 pieces of information. But functions can only return one thing. So we do a little trick. We go ahead and pass back the array, but to get the length, we pass in a pointer to an integer, and then the read card function will fill in that integer for us. So when we return from read card, we'll have the array, and we'll also have the length filled in for us as a variable. So this is a kind of a typical way that C programs hand back or return two or more things to the caller. One of the items gets returned as a return value, and the remaining items get returned as parameters that were given to the function that the function fills in. I'll show you how that works in just a moment here. You also have a function called SaveJPEG. You give it a pointer to where the JPEG begins, its length, and what file name you want to write it to. And then it'll take care of just dumping that data to a file in the file system. And then finally, there's a function called recover. This is where the bulk of your program is going to happen. You give it a pointer to where the disk image begins and its length, and then inside of that recover function is where you're doing all this work to scan for the beginning of a JPEG, find the end of it, and then call SaveJPEG. So right here it says determine where the scan through the array, look for the signatures, the beginning of JPEG files. When you find one, determine where the end of the image is, calculate the length of the data, construct a file name to save it as, and then call SaveJPEG. Okay, well, it's a lot of stuff, but let's go over this program itself. So here's the three functions: read card, save JPEG, and recover. So here's how, and you don't have to worry about this. Read card is already going to be called for you, but I'll just show you how it works. Here's the call to read card. Here's the name of the file, which is a define up here. And then here is a pointer to the card length, which is just an integer. Okay? And then we get handed back a pointer to the card data. Here's read card. And very quickly, I'll walk you through this code. You actually don't need to know anything about how this code works. All you have to know is that after read card is called and it returns, you'll have the data sitting in the card data array, and you'll have the length sitting in card length. Okay, so you don't have to know how read card works, but I'll show it to you anyway because you're probably curious. So the first part of it up here determines the size of the file. It asks the operating system, how big is the file? It uses a function called stat to figure that out. And then it sets aside memory corresponding to the length of that file. So if the file is, let's say, 1,000,000 bytes long, then it will ask the operating system, set aside 1,000,000 bytes, and then it will use that as the place to fill in the card data. The next step is to open the file for reading, and then pull in all the data. So it pulls in from the file, puts it into the array, and it does the entire length of the array all at once. And then it closes the file, and then it returns to you a pointer to the contents of the file, and it fills in the length right here. Let's see, the question is, could I have done this by returning a struct? Yeah, I sure could have done that, but then we would have to learn about structs first. And we haven't learned about structs yet, so this is the way we're going to do it. I'm using this return technique, not only because this actually gets used by some of the C library functions, but also because we're leveraging things we already know here, which is pointers and arrays, and we don't have to use anything new like a struct. Okay, and then here's Save JPEG. Again, you don't have to worry about how this program works, but I'll walk you through it anyway. You give it a pointer to where the JPEG begins. You tell it how long it is and what file name to write to, and then it just opens the file for writing. It writes the data to the file, and then it closes it. It's really simple. Okay, so the bulk of your program is going into this function called recover, which you need to write yourself. You pass it in a pointer to the card data and its length, and then it goes to work. I suggested in the assignment that when you construct the name of a file, you use something like sprintf. We already know about printf. Printf is this nice general purpose, print something to the screen. There are other variations on sprintf. There is fprintf, which is used for printing not to the screen, but to a file. And then there's also sprintf, which is used to not print to the screen, not print to a file, but to print, quote unquote, into a string. And so sprintf is a great way to format strings the way you want them. Like in Java, all you have to do to construct a string is like use the plus operator to join stuff together. But in C, we can't use that. We don't have the plus operator to join strings together. So we can use sprintf to build a string out of variables that we want to insert into the string. So let me show you how that works. Let me just write a quickie little program for you. I don't know what to call this. sprintf demonstration, sprintf demo.c. So I've got a string here that is just 20 characters long. That'll be big enough for what we need to do. And then let's just write a loop. Here, let's go for int I equals 0, I is less than 10, I plus plus. And then let's use sprintf to print into that string I want to print that number I plus something else. Let's just go like a hello %d exclamation mark. Okay, so what sprintf will do is it'll take this string, it'll replace the %d with the value of I, and then this string will go into this string variable. So it won't go on the screen at all. It'll go into this this string, and then I could print it out, right? Okay, so what good is this? I could have just used printf in the first place to just print it out, but I wanted to show you how you can format a string using sprintf. So we can take variables, insert them into the string, store them in the string, and then, here I happen to print them out, but what you're going to use in your program is you're not going to print out the file name, you're going to use that as a parameter to save JPEG so that it goes into a file name that starts like image1, image2, image3, starts with image, and then has a number. So that when you save each one of the JPEGs, you'll get a file name with a serial number on the end of it. Okay, so I want you to get started on this assignment, but I don't think you will be 100% successful in your first attempt at it, or even your second attempt, or your third attempt. I want you to get started on this, and then when we come back on Tuesday, hopefully enough of you will have started it that we can talk about problems that you've run into and how to solve some of these problems. There is no one way to write this program. There's no like one best way to do this. I wanted to do this as a way for you to creatively think about how to solve this problem, and then just do the best that you can. And then we'll talk about it on Tuesday. We'll see how far you got, and we'll talk about problems you're running into and see if we can come up with some solutions to them. The very last thing I'll leave with you is I have no idea where to begin. So here's what I would suggest. You've already got a template program. You're going to start your recover function, but all you're going to do is just identify the beginnings of each one of these JPEGs. And then just count them up. How many times do you see that 4-byte sequence appear? And just print that number out. And then at least you'll have some idea about how many JPEGs are on there. And I'm not going to tell you right off the bat how many the number is, but I'm going to tell you the number is between 20 and 40. So if you get a number between 20 and 40, you know you're on the right track. For those of you who are watching on YouTube who want a copy of this file, again, let me think about how I can get this to you. Yeah, let me think about that. I'll be able to post this somewhere where you can get to it, and then I'll put it like in the YouTube comments, like some kind of Dropbox or something. Let's see. Oh, you're asking like, how did I actually do this? So the way I actually did this was, I actually went around and took pictures using a point and shoot camera, and then I pulled the SD card out, put it in my computer. It wasn't really corrupted, but I used a command on a Linux system called, also on the Mac, called DD, data dumper. And I can pull the data off of the disk, and I can dump it into a file. And so I used the DD command to pull that data off of there. And yes, this assignment is very similar to one of the Harvard CS50 assignments. I've adapted it a little bit, so it's not completely identical, but the spirit is the same. So I actually found the instructions, the instructor directions for this assignment about how to logistically do this assignment. Like, how do you actually create this image file and make it available for students to use? So thankful for Professor Malin for walking us teachers through how to do this assignment on the back end and prepare it for students to use. Okay, so I think that's enough for today. Again, try to just get started on this. See if you can print out the number of images that you found. Do keep in mind that the start of a JPEG image is only going to be found at a block boundary. It's only going to be found at a multiple of 512. So what you're probably going to have inside of your recover function is a loop that goes from the beginning of the image data or the disk data all the way to the end, right? It's going to count from 0 up to card length. But it doesn't have to go byte by byte. The start of a JPEG is only going to be found at a 512 byte boundary. So you could write your loop not to increment I by 1, but to increment it by 512. So your loop might look like this. For int I equals 0, I is less than card length, I plus equals 512. So we can bound through the data 512 bytes at a time, rather than one byte at a time. That'll like make the room, I mean, the loop will still run pretty fast because the file's not that big. It's about 16 megabytes, but this will greatly cut down on the amount of work it has to do. Oh, welcome to the program, 50Cal. I'm sorry you were a bit late, but I'm glad you were at a job fair. Tell me again, where is it you are? Like, roughly the part of the world you're in? And then while you're answering that, let's see, any other questions here? Yeah, you got all sorts of questions about disk drives and storage. Are SSDs as fast as RAM? No, they're a lot slower than RAM, but they're a lot faster than the old spinning hard drives. So they're somewhere in the middle. That's why computers still have RAM and they still have SSDs. I mean, if SSDs were as fast as RAM, we would have just gotten rid of RAM. Just forget it. Not using that anymore. Just use SSDs. But they're not. They're still a bit slower. But the capacity of an SSD is much larger than RAM. You know, realistically, you can probably only afford 16, 32 gigabytes in your computer, but your SSD is going to be a terabyte for roughly the same cost, right? You know, 16 to 32 gigabytes might cost, $100 US, give or take a little bit. And then that 1 to 2 terabyte SSD will also cost about $100 US. And so if you kind of use that as your benchmark, how much storage can I purchase for $100? You'll see that RAM has a trade-off, right? You can't afford as much, but it's way faster. And SSDs, you can afford more, but they're slower. And then these spinning hard drives, they're way slower, but again, for about $100 US, you can purchase something that's 16 terabytes, ballpark figure. And then within the processor itself, there's a small amount of cache memory that's really super fast memory. But for that $100, you can probably only afford to buy maybe a megabyte of that stuff. Now, is something like the virtual memory stored on the disk drive? Yeah, it is. So when you have that swap partition or swap file, that's also stored on the SSD or the disk drive. And that could also be an interesting thing to look at. The forensic investigators might look at that swap file and go, well, that basically is an extension of memory. And so some of the data in that file may be stuff that was in memory previously. So that could be an interesting thing to look at. Ah, you're in New York. Okay, so good. A job fair. I hope that was successful for you. Hope that that is productive and you got something out of it. Like actually a job. Okay, so I think that's about it for today. Each type of memory then uses completely different technologies internally. Yeah, most likely. So your dynamic memory inside the computer uses basically an array of capacitors to store the charges. So they're slower. The one inside of the processor might use transistors to store the data, so those are a lot faster. And then SSDs use again, they use some kind of like transistor method, but these transistors can store their state even after the power is removed from them. So they make a physical change within the structure of the cell itself. And that's why they have a limited lifetime, because there's only so many times you can flip those bits back and forth before they just wear out and don't work anymore. And then for a disk drive, they use magnets, basically. These platters are magnetic, and then the read-write head here is changing the magnetic field inside of the structure of the platter. But because nothing is really physically changing, inside. They essentially have a almost unlimited lifetime of the number of times you can flip the bits on them. So disk drives are a lot more durable. They'll last longer than an SSD. An SSD will eventually wear out. And the way it wears out is not like the whole thing just crashes all at once. The SSD controller will read and write data. As it reads data off of the cells, it might go, oh, that data didn't come out very cleanly. There's some error correction built in, so it's able to recover the data that it didn't read correctly. But then it may say, okay, since I got an error reading that cell, I'm never going to use that cell again. So I'll just mark that one as being unusable. And then what that does is it reduces the capacity of your SSD by 1 cell at that point. You can no longer use that cell, and so the capacity of the disk drive or the storage device gets a little bit smaller. So over time, the total capacity of an SSD gets smaller and smaller and smaller until it fills up, and then you can't use it anymore. So yeah, all these storage devices use completely different technologies, and that's why you get the trade-off. Right? Some technologies are more expensive, but they're faster, and some of them are cheaper, but they're slower. Some technologies, like the magnetic stuff, you can high density data on them. You can pack a lot of data into these things. SSDs, not quite as dense, but faster. Best way to delete a file is to write a different file again and again until that old file trace is completely removed. Yeah, if you do something like a secure delete on your computer, and sometimes that's an option available to you, then what it does is it doesn't just mark the block as deleted or block it as free. It actually goes through and writes like random ones and zeros to that block a few times just to completely wipe out what was there. And the reason why you have to do it a few times is even if you just wrote a bunch of zeros, there's still like a little bit of residue. It's particularly if it's a spinning hard disk like this. There's still a little bit of magnetic residue left over from the old value that was there. And so really sophisticated investigation equipment can go and recover the actual magnetic flux off of the platter and recover the data that was there. So you write a whole bunch of ones and zeros, random ones and zeros a whole bunch of times, and then that flips the bits back and forth enough times that the magnetic residue is no longer there. But it makes deleting a file a whole lot slower. Is swap memory on the disk drive a security risk? Yes. And security experts will tell you that once an intruder gains physical access to your hardware, pretty much all bets are off. There's nothing stopping a determined attacker from physically removing the data. I mean, physically reaching into your computer and pulling the storage device out and then taking off with it and doing with it whatever they want to it. So, is swap memory on the drive a security risk? Sure, but that means that they have physical access to your disk drive, and then who knows what else they could find. So at that point, it just becomes a matter of time. Like, how long can you hold the attackers off? And that could have to do with, like, I guess in a really secure data center, they might have, who knows, they might have like armor plating on the racks that hold the server equipment just to hold off a potential attacker a little bit longer, because now they have to use more sophisticated equipment to break into it. But once they have physical access to it, security goes out the window. There was even a research project a few years ago where, I mean, you probably know that once you remove power from a RAM chip, its contents essentially is erased, right? Because they're capacitors, they hold a charge. But if they aren't periodically refreshed, then that charge dissipates. And so you've been told that once power is removed from RAM, its contents are erased. But it doesn't happen instantaneously. It happens slowly, like over a few seconds, for that charge to dissipate. And so if you turn off a computer, the content of its RAM don't just disappear instantly. It takes a little bit of time. And so what these researchers showed was that if you took a computer, a laptop or something like that, and you remove the power from it, so you physically disconnected the battery, and then you froze the RAM chips by spraying a coolant onto it, that you could delay the decay of the data by enough time that you could pull the RAM chips out. You know, they're just little cards that slip into the computer. You could pull them out, put them into another computer, start up that computer, and it would be as though the computer had never been shut off in the first place. Right? That's freaky, right? Right? So you remove the power from the first computer, you freeze the RAM chips, like physically spray like what is it, liquid nitrogen onto them to make them as cold as possible. And when you make the chips cold, they hold their charge longer. Then you can pull the RAM chips out, put them in another computer, and start that computer up. Actually, what they did was they didn't start the computer up. They put it in another computer. That computer would then turn on and then would scan through the contents. So it had its own memory. So this RAM you were adding to it was in addition to the existing memory. And then you just scan through the contents of that new memory and pull off any data that you could find. And so what they were able to show was they had loaded an image into the memory of the first computer, turned that computer off, froze the RAM chips, put it into a second computer, started that computer up, and were able to recover that image data. Yeah, kind of like a heart transplant, right? And so the upshot of this research was to say, if you are using a computer that has proprietary, confidential data on it, and you turn it off, stay with the computer for a couple of minutes, because that's the vulnerable time. That if you turn off your computer and then you step away from your desk or you go get a coffee, an intruder could come in and snatch that computer and very quickly pull the RAM chips out, put it in another computer, and get some of the data. And so they said, stay with your computer for a couple of minutes just to make sure that no one grabs your computer during that time, and that the RAM chips have a sufficient time to discharge and then lose their contents. That was the takeaway from their research. Will encrypted hard disks help? Absolutely. That seems to be the default now in most operating systems, particularly on the Mac. And I think also on Windows, that all the data on your hard disk is now encrypted, going in and out. So if somebody does physically get access to the hard disk, it would be very hard to get the data because they would have to decrypt it using a key that they don't have access to. But that doesn't mean that the attacker couldn't just throw as much computing power as they could get their hands on at the problem and eventually be able to crack it. The problem is that the encryption routines used these days use keys that are so large that it would take like age of the universe to figure out what the key is. And no amount of computing power will reduce that number by enough time to make it practical. What was interesting about the story about the RAM chips? I'm doing a quick Google search to see if I can find this paper. That wasn't it. What I found was this paper called Study of Data Retention Behavior in Modern DRAM Devices. So that's pretty similar, but I remember the paper actually having a picture of the images that they had recovered off of these chips. Scanning through. So this is a presentation. Maybe this is it. Maybe this presentation is going to have those pictures I was thinking about. No, I'm not seeing anything yet. Let's look at the same images that were in their research paper. Same graphs and stuff like that. Same charts. No, that's not it. This one? Well, don't have access to that. Is it this one? There seems to be a whole bunch of papers here, kind of about the same thing. So, I must be on the right track here. Anyway, I'm not finding it off the top of my head here. No, I'm not seeing it. I think it was a picture of the Mona Lisa, of course, as their experimental image they used. And so that's what I'm kind of like looking for. It's like, do I see a picture of a degraded Mona Lisa here? And I don't. So anyway, that's the idea. Can you recover data off of a RAID device? Sure. I mean, if you know how the RAID storage was set up, then you should be able to reconstruct that if you have all or most of the storage devices from a RAID cluster. So if your RAID has four drives in it, but you put the drives in like the wrong order, then you're not going to get the data off of it. But if you put them back in the right order, then you should be able to get the data off of them, even though the data is now split across multiple devices. Okay, well, we could talk for hours about this stuff. Why don't we end it here? And I will see you on Tuesday or Monday if you want to learn about modern cryptography systems. Actually, I'll end the Zoom stream now because those are my students and they're going to watch that and they don't need to know all this other stuff. So I'm going to say goodbye to the Zoom people. And then now, who's left is the YouTube folks. And yeah, you can come back on Monday and we'll start talking about RSA, the modern cryptography system that uses integers and big numbers to protect your data. And then on Tuesday, what are we doing on Tuesday? Well, we're talking about the CSI assignment. And we'll see how many questions there are about that. And then from there, we'll see where we go. But I know that at some point next week, we're going to also start talking about version control systems. So whether that happens on Tuesday or Thursday, I'm not sure. We'll kind of play it by ear. All right. Well, I'm glad all of you could make it, and I hope Cal 50 that you do get some kind of lead on a job. And I will work today or tomorrow on figuring out how I can make this material available to you. Okay, have a good day, everyone. I'll see you next week sometime. Take care, have a good weekend, and I'll talk to you later. Bye-bye.